As we delve deeper into derivatives, we will find that there are some theorems that will allow us to find information more quickly than we've been able to do so far. Hi, my name is Tom Atwater, and in today's lesson we will examine the first and second derivative tests. Let's start by taking a look at the first derivative test. The following test applies to continuous function f of x at a critical point C if f prime changes sign from positive to negative at the point C, then f has a local maximum value. And so I want to show you, for f prime, we're looking at the slopes. That is the derivative, the slopes. And what you'll see is that the slope is positive where I've drawn it. And what's going to happen is right at C, it's going to, or right after C, I should say, it's going to start to change to the green lines, which have negative slopes. And so what's happening is we've got positive slopes changing. Right at C, it's at 0, of course, and then we have negative slopes here. So it's changing from positive to negative, and that means we have a local max. If we did the same thing on this side, you would see, again, positive slopes, and then a very abrupt change into negative slopes. All right, let's take a look at minimums. If f prime changes from sign from negative to positive at C, then it has a local minimum point. So once again, you can see very quickly we have our slopes, which are negative, and then when they cross at C, where it's exactly 0, they then become positive slopes. And so we see that we'll have a local minimum point here. And the same would be true for our other curve. Even though it's straight lines, you can clearly see those are negative slopes. At C, it all of a sudden, or just beyond C, it becomes a positive slope. Now let's take a look at what happens when there's no sign change. If f prime, first derivative, does not change sign at C, then f has no extreme value at C. Very quickly then, you can see that the slope here is positive. Here's this point where something happens, but the slope continues to be positive. So there's no sign change there, and therefore there is no extreme value. Now let's take a look at a left endpoint, which we've labeled A. If the first derivative for x being greater than A, then x has a local maximum. So let's look at this picture. What we have going on is, here's our A value. We're saying that the first derivative is negative, i.e. the slopes are negative, and we're looking at x values which are greater than A. Then what happens is we have a local maximum point. If I read this in the parentheses instead now, and we say that if the first derivative is positive, then we're going to have a local minimum point. And that's the graph here. First derivative positive. I have slopes which are positive. Here's my A. That will be then a local minimum. Now let's take a look at what happens if we have a right endpoint B. And what we find here is if f prime, the first derivative, is less than 0, for x being less than b, then we have a local minimum at b. So let's look at the left-hand side picture. We have first derivative having slopes which are negative. We're looking at x being less than b. And so what happens is we get a local minimum point at b. Now, if I go through and talk about the parentheses, if we have a first derivative which is positive for x being less than b, then we will have a local maximum. And that's the picture we have here. We have the first derivative, that is the slopes are positive. We're looking at x being less than b, and so we have a local maximum point. Let's look at an example of where we can apply some of these theorems that we've looked at. Let's use the first derivative test to determine the local extreme values of the function and identify any absolute extrema and support your answers graphically. What we have is y equals 2x to the fourth minus 4x squared plus 1. So we want to apply the first derivative test, which means we have to find the first derivative. So let's take and find y prime equals, well, this would be 8x cubed minus 8x. And now for the first derivative test, we need to know when is that equal to 0. So we set it equal to 0 and solve it. I can factor out 8x, which leaves me with 8x squared minus 1. So my two factors, this would lead to me to say that x equals 0, and this leads me to x equals plus or minus 1. So those are our critical values that we're interested in, the local, our extreme values. We don't know what they are yet, but that's what we're going to be looking at. Those are the extreme values that we need to check out. So what we can do is look at a number line. Here's 0, here's 1, and here's negative 1. What we're interested in is what is the value of the first derivative at these points. And what we have is the first derivative here will take some point, arbitrary point, like for instance negative 3, and plug it into here and plug it into there, and then evaluate it. However, I'm going to show you something that mathematicians do a lot. If I look at the factored form, it's actually a little bit easier to figure out if it's positive or negative. Because all I do is negative 3 in here. I don't even care what it works out to be as a number. I just care that it's negative, right? And the same thing here. All I care about is if this is positive or negative. Well, of course, if I take negative 3, that's negative. Here, it's positive. A positive times a negative tells me that in this particular interval, the first derivative is negative. Well, now let's look inside here, here, and here. And we'll do the same thing. So pick something like negative a half, and when you plug it into here and here, we'll find out that that's positive. And if I pick 1/2 here and plug it into here and here, we'll find out that overall it's negative. And then if I pick a number like 5, plug it into here, we'll find out that it's positive. So now we know what's happening with the first derivative. It's changing from negative to positive, from positive to negative, and then back again from negative to positive. Well, what does that all mean? What it tells us is that at x equals negative 1, this point right here, we're going to have, and I'm going to just sketch something for you, it's going to be some kind of local minimum. And at x equals 0, because it's changing from positive to negative, right, we're going to have some kind of a maximum. And then again, it's changing from negative to positive at 1, so we're going to have some kind of a local minimum. And the other thing that I can say is that there's no other sign changes here. So in fact, this value and this value are both going to be absolute minimums. And the way we can find out what they actually equal is to take the 1 and plug it back in here for x. When we do that, and I won't bother to do the arithmetic, but we will get y equals negative 1. So the absolute minimum value is y equals negative 1. Let's take a look at the graph to see if it supports these local minimum and the local maximum points that I've described to you just by using the first derivative test. So here's the graph. And look at that. Of course, it totally agrees with what we found. We have a local and minimum points at -1 and +1. We have our local maximum point at 0. And there, of course, were no other sign changes. And we can see that the value -1 for y is our absolute minimum value. All right, let's move on to concavity. With concavity, well, let's define it first. The graph of a differentiable function, y equals f of x, is A, concave up if on an open interval I, the first derivative is increasing on the interval. And it's going to be concave down on the open interval I if y is decreasing on the interval. Let me draw a few sketches to illustrate this concave up and concave down for when y is or the first derivative is increasing and decreasing. If I have two graphs which are examples of concave up, they could be these two graphs right here. And if I look at what's happening to the first derivative, it means I want to look at what's happening to the slope of the tangent lines. So here, I can see that what's happening is the slopes are getting steeper, which means, of course, that the first derivative is getting larger. And over here, these are negative slopes. And what's happening is, although they're getting flatter, that means they're getting less negative, i.e., they are increasing. So you can see that for concave up, we do have that the first derivative is increasing. Well, what about concave down? Let me draw a couple graphs of concave down. That would be one of them, and my other one going the other way. Let's take a look at slopes of those tangent lines to see what's happening again. So if I have a slope here, we're positive. Take a slope there of the tangent. Well, what's happening is it's decreasing, right? So we have the first derivative decreasing. We have a concave down. What about negative slopes? Well, we have negative slope. This is a negative slope here. And then it's getting steeper, which means it's getting more negative. The absolute value of the numbers is getting bigger, which means that in terms of the negative number itself, that it's decreasing. And so that gives us a concave down. All right. If y equals f of x, the function has a second derivative, we can conclude that the first derivative increases if that second derivative is positive. And the first derivative decreases if the second derivative is negative, which is going to give us what's called the test for concavity. The graph of a twice differentiable function, y equals f of x, is concave up on anywhere in the interval where the second derivative is positive. And it's concave down on the interval where the second derivative is negative. The points on a curve where the concavity changes are called points of inflection. Let's take a look at the definition for points of inflection. A point where the graph of a function has a tangent line and where the concavity changes is a point of inflection. Let's look at an example where we find a point of inflection. Use the concavity test to determine intervals on which the graph of the function is concave up and concave down. The function we're going to look at is y equals 2 times x to the 1/5 power plus 3. So let's find the first derivative and then the second derivative. Y prime, the first derivative, is going to be equal to 1/5 times 2, so 2/5, times x raised to the 4/5 power. The second derivative is found by the same process. Take the negative 4/5, multiply it times 2/5, and we get negative 8 20/5 times x raised to the negative 9/5 power. Now, in particular, for the value x equals 0, the second derivative is undefined, which tells us that something is happening at 0. So I'm going to use that to say, let's look at what happens to the left of 0, like for negative numbers. Y double prime for any negative number, for instance, take negative 5. When we plug a negative in here, when we raise it to that whole power, it's still going to remain negative. Multiplied by the negative, that means that this is positive. So by the same reasoning, if we take y double prime of some positive number, for example, 7, it's still positive here times this negative. This will be negative. What that tells me here is that this is going to be concave up, and this is going to be concave down. Then in terms of the graph, this is just a very rough sketch. We know that for negative, it's going to be concave up. But then something happens at 0 where beyond to the right, it's going to be concave down. So that's how we can use that second derivative test to help us draw the graphs of functions. Let's try another example. Let's take the example to find all the points of inflection for the function y equals x times e to the x power. To do this, of course, we need to take the first derivative, and let's do that. And after we do the first derivative, we'll find the second derivative. So in this case, y prime, we have to use the product rule because it's a function x times e to the x. So it's the first times the derivative of the second, and remember the derivative of e to the x is e to the x. Plus, we now take the second function, which is e to the x, and multiply it by the derivative of the first function, which is x, and of course the derivative of x is 1. So that's y prime. Let's look at y double prime. Y double prime. Well, we again have to take the derivative of x times e to the x, but we just did that, so we know that this is the answer to just this section. So it's x e to the x plus e to the x. But then we have to do the derivative of that, so the derivative of e to the x is e to the x. So this time, what we have in terms of the second derivative is y double prime equals x e to the x plus 2 e to the x. And then I can factor out the e to the x. I'm going to set this equal to 0 because what I want to know is what's happening with the point of inflection. And so I have e to the x times x plus 2. And that equals 0. And it equals 0 when? Well, when x is equal to negative 2. So the second derivative is equal to 0 for x equals negative 2, which tells me that that's going to give me my point of inflection. But what's the actual point? I need to take this number and plug it back into the original function, y equals x times e to the x. So my point of inflection would be this. Negative 2 is the x value, and the y value, I plug negative 2 in here and here, so I get negative 2 e to the negative 2. And that's my point of inflection. Let's move on to the second derivative test for local extrema. And to do this, we're going to look at a theorem. And the theorem is the second derivative test for local extrema. If the first derivative is 0 and the second derivative is negative, then f has a local maximum at x equals c. If the first derivative is 0 and the second derivative is positive, then f has a local minimum at x equals c. Let's look at an example where we apply this. Use the second derivative test to find the local extrema for the following function, y equals x e to the x. And I picked this because in terms of doing the derivatives, we already know the answers, so we can go a little bit quicker with this. We know that the first derivative was x e to the x plus e to the x. And I can simplify that a little bit by factoring out the e to the x, which leaves me with x plus 1 in parentheses. And then what I can do is set that equal to 0, because we want to know, using the second derivative test, we need to know when is the first derivative 0. Well, when is it 0? It's 0 when x equals negative 1. Now I need to find the second derivative, which we've already done before. Y double prime, remember we said, was equal to e to the x times x plus 2 in its factored form. And now what we're interested in is, what is the value of the second derivative evaluated when x is equal to negative 1? And in that case, the second derivative is going to be positive. That is, it's greater than 0, because when we stick negative 1 in here, this is positive, and of course this is always positive, and therefore the second derivative in this case is greater than 0, which means that we have a minimum point. And in order to find the actual point that the minimum point is, we need to take the negative 1 and plug it in here. So our minimum point occurs at x equals negative 1, y equals negative e to the negative 1. Well, now it's time for you to try a problem. And the problem that I would like you to work on is this. Use the second derivative test to find the local extrema for the function f of x equals x cubed minus 12x minus 5. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Okay, let's find out how you did on this. The function f of x equals x cubed minus 12x minus 5. What we need to do is find the first derivative and second derivative. So the first derivative, f prime of x, would be 3x squared minus 12. And we need to know, when does that equal 0? Well, of course, this is 3 times x squared minus 4. Set it equal to 0, and we find that it's when x equals plus or minus 2. So we know those are the points we're going to check out. We need to find the second derivative. F double prime of x equals 6x. Of course, the 12 is a constant, so it goes to 0 when we take the derivative. Therefore, f double prime of not of x, but of, let's take 2 first, is going to be equal to 12. And of course, 12 is positive, and that tells me that I have a local minimum point. Now I take f double prime of negative 2, and that's going to give me negative 12, which of course is less than 0, and that tells me that here I have a local maximum point. Once again, if you wanted to figure out what the actual y value is, you would have to take the 2 and plug it back into the original formula or the original function, and then that would actually be the y value that is the maximum or the minimum, depending on which x value you plugged in. Let's use all of the things that we have talked about so far in today's lesson to work an example. I want you to take, what we're going to do is take the function f prime of x, which equals 4x cubed minus 12x squared. So we're starting with the first derivative, and we're going to identify all the extrema of f. Then we're going to find the intervals on which f is increasing and decreasing. Then we'll find where the graph is concave up, where it's concave down. And finally, we'll sketch what could be a possible graph for that function f. So we were given the first derivative. Given the first derivative, what we know is we set it equal to 0, and that's going to give us our critical points. So let's start with that. Equals 0. And we can factor 4x squared, which will leave me with x minus 3. That's equal to 0. That tells me that the critical points that I have are 0 here and positive 3 there. If I think of the number line and I put 0 and 3, I now know that there are 3 intervals that we need to check out. We need to check out less than 0, so pick some number out here like negative 5. When we plug that in for x here and here, this, of course, will be positive. This will be negative, which tells me that in this interval that the first derivative is negative, and therefore it's decreasing. In this interval right here, pick something like negative 1. That'll be positive. This will be negative. So it's negative here, which means that it's still decreasing at that point. And then finally, let's pick a number that's out in the beyond 3. And when we plug it in, we'll find that it's positive, which means out in this interval, it's increasing. Now let's find the second derivative. F double prime of x is going to be 3 times 4 for 12x squared, and then minus 24x. Once again, we want to set that equal to 0. And in this case, we can factor out a 12x, which leaves me with x minus 2, which equals 0. And this time what I have is x equals 2. I'm sorry. I need an x right there, don't I? Let me sneak it in there. So 12x times x minus 2. That tells me that x is 0 and x is 2. I want to do the same thing that I did here in terms of a number line. So let's get a clean screen for me to do that. And I will rewrite that my second derivative was equal to 12x times x minus 2. And so I remember that, and we now have the points 0 and 2. We have 3 intervals. Once again, I'm using the factored form because it's a little bit easier to figure out where it's positive and negative. If I take a number in this interval like negative 5, that would be negative, that would be negative. Negative times a negative gives me a positive. What that tells me is this is concave up at that point. Pick something here like the number 1. When I plug it in, it's going to be negative, and that tells me that it's concave down, which I'll just use a D for that. And then out here, we will find if we plug in something like 10 that both of them are positive. So this is positive, and that means that it's concave up in that interval. Okay, so now taking all of that information together, we know that we have certain points that we want to graph, and let me show you what a possible graph would be for this. Remember that we had those three particular values. We had that x was equal to 0, we had x was equal to 2, and x was equal to 3. And we are looking at when we discovered that it could be concave up, when it was concave down, and again when it was concave up. And yes, there are other possibilities, but they all have to have that general trend to them. They can vary in terms of how steep you make them, but that's what we would have for the graph. All right, great. Well, in this lesson, we explored the first derivative test, the second derivative test, points of inflection, concavity, concave up and down. So be sure to work the exercises that your teacher assigns, and we'll see you next time.